So we have two students who are presenting papers, which means they're going to be given 12 to 18 minutes or something like that by their organizer. We've asked them to keep it to 15, but they thought 20, so that's the first challenge here. So we'll try to keep you to about 15 minutes, and we'll have a few minutes after each of these talks for questions, and that will take us to 12:45, and then we'll have about 20 minutes for the two talks that are going to be posters. So we ask those students just to give 5-minute talks. We don't really have to worry so much about their talk, but we can talk about the science, then we can talk for a couple minutes after each of those. So welcome everyone to our first ever visiting student practice PAA combination super brown bag. So we have Paul Chung, paper co-authored by another student. Paul is a student in the joint PhD program of sociology and demography, and we're delighted. So take it away, Paul.
All right. Hello, everyone. My name is Paul. The work I'm about to present to you today is done jointly with Peter Hepburn, who's also a member of the department, but he's currently in New York City, but he sends his best regards. Today I'd like to talk to you about kin availability in the era of mass incarceration. And this is the first draft of these slides, so excuse any rough edges. Okay, so let's begin. Is there a way to... So let's begin by talking about mass incarceration. What do we mean when we use this term mass incarceration? In a nutshell, this is what we mean, this historically unprecedented increase in the national rate of incarceration that occurred between 1970 to 2000 roughly. Up until 1970, the rate of incarceration in the United States remained relatively consistent at around 200 per 100,000 resident population. So that's about 0.2% of the total US population behind bars. Just 30 years later, that number jumps to 915 prisoners per 100,000 resident population, or about 1% of the national population behind bars. And so what set off this spike in incarceration? Most experts writing on the topic kind of peg it on Nixon's war on drugs. And I won't go too much into that. All right, so as a historical phenomenon, this is very interesting, but why, as social scientists today, should we care about mass incarceration? One reason we might care is because this incredible increase in the rate of incarceration has occurred differently depending on your particular race group that you're observing. And so to illustrate the point, what I've done here is plot age-specific rates of incarceration separately for Black and white Americans in 2000, the male populations. And what we see here, of course, is the Black population, the Black male population is at much higher risk of being incarcerated than the white male population. At the point of widest divergence, this age category of 25 to 29, Black males are about 8 times, a little bit over 8 times more likely to be incarcerated than their white peers. And just to put this into context, that's about 10% of all Black men ages 25 to 29 in the United States in 2000, compared to just about 1% of white men in that age category. So those are rates. If we were to aggregate and look at absolute numbers, so if we add all the prisoners across all the age categories, Black male prisoners outnumber white male prisoners almost 3 to 1. And keep in mind, in 2000, the Black population in the United States represented just 12% of the total US population. Okay, so at this point, if you're a particularly callous observer, you might continue to ask, so what? Racial inequalities aside, in absolute numbers, that's a very small fraction. Prisoners are a very small proportion of the total US population. A, and then B, they're prisoners, so why should we care? Well, one reason we might continue to care is because the burden of incarceration is rarely borne just by the prisoner themselves. Prisoners are embedded in large networks of family and friends who help them kind of reintegrate and kind of reestablish life following prison. And so we care about mass incarceration because it has consequences for the family. We can think of these family consequences of incarceration as falling into two types, or two categories. The first we might call collateral consequences. And these are consequences, this has to do with the way that incarceration constrains the ability of prisoners to provide support for their family members, their dependents. And so kind of these missing men studies or these children of the prison boom studies, all of these kinds of studies are looking at these types of consequences, where the focal ego is the prisoner's family, not the prisoners themselves. The second type of consequences have to do with reintegration support. So this has to do with a family's ability to reintegrate members who have recently been released from prison back into society. And so a lot of studies have found that people who exit prison and then kind of re-enter society, who come back to strong and good family networks, do just much better, and they are much less likely to go back to prison. Same studies also find that oftentimes a lot of family networks are not that robust, and especially if there's high prevalence of incarcerated members within those networks. And so this class of consequences takes as its focal ego the prisoner returning from prison, trying to re-enter society via their family. So to recap, two types of consequences of mass incarceration on the American family. One, it constrains the ability of prisoners to support their family members, and two, it constrains the ability of family members to support formerly incarcerated members. So a lot of good research has been done on each of these two domains of family consequences, and most notably by Bruce Western and colleagues over the last several decades. So what more can we add to the mix? Well, existing research tends to focus on prisoners, their partners, and their children. And while these relations are very important, they represent only a small fraction of the total kind of kinship networks within which prisoners are embedded. And so when we talk about family, what we're thinking about is way more than just your spouse and your children. It's all of these kinds of relations that we have in our heads. And so though this is purely schematic, it should give us a sense of just how much we're missing if all we pay attention to are partners and children. And that's kind of the information that's available in the existing literature. And to be fair, the reason why that is because the data recording these additional kinship linkages simply don't exist in the data. The most common survey instruments that are used to study incarceration in the family have, I think, maybe two limitations. One, they are, again, they only kind of record information on these close kin, these partners and children. And two, they're cross-sectional, and so they don't offer any kind of longitudinal follow-up. So what that means is that given the best data that we have available to us, we are unable to kind of get a good sense of the total prevalence of incarceration within entire kinship networks, and we don't know how those prevalences might change over the course of life. So Peter and I got together and we started thinking, is there a way around kind of these data constraints? And the results of that brainstorming is this project. Okay, so in summary, what we do in this project is we use microsimulation to overcome the data constraints we discussed earlier. And I'll discuss what that is in just a second. We use the resulting microdata to construct estimates of kin incarceration, and by that, all I mean is the incarceration of your relatives, so your Aunt Jody going to prison. And we do this for two historic birth cohorts, and I'll talk about which birth cohorts those are in a second, and we do this stratified by race. And finally, we use those estimates of kin incarceration to measure these two kind of family consequences that we talked about earlier, collateral consequences and reintegration support. Okay, so microsimulation. What microsimulation does in a nutshell is that it allows us to input population level rates and get out individual level data. And so in our case, what we do is we input mortality rates, fertility rates, incarceration rates, aggregate rates, And then within the machine, SOCSIM produces fictive individuals that then are born, reproduce, get incarcerated, and die in accordance with those population level rates. And at the end of the simulation, what we're left with is complete microdata on each of those individuals, including complete genealogy, so we know how each individual is related to every other individual in the simulation, and their full incarceration histories. And we simulate two cohorts. One is what we call the boom cohort, those born in 1960 to 1970. And these are the folks that are reaching adulthood just as the prison boom is really like getting going. And then the second cohort we simulate is the post-boom cohort, those born in 1985 to 1995. And these are the folks that are being born and are coming of age during the height of the prison boom. And so what we're really interested in is this kind of period, if you recall, between 1970 to 2000, kind of when mass incarceration was occurring. And so if we use that as a reference point, then we can loosely think of these two cohorts as the parent generation and the child generation. And so these cohorts end up becoming very convenient for the two types of consequences that we're interested in. One is the reintegration support. Recall that's looking from the perspective of the adult prisoner re-entering society. So that makes sense to peg that on the boom cohort. And then collateral consequences are those that accrue to the family members or dependents of this generation. Okay, so let's look at some results. First, we'll start with collateral consequences. Those consequences accruing to the dependent members of prisoners' families. And so what I've done here is I've plotted risk profiles of relatives going to prison. So all I mean by kin's first incarceration is the first time that Aunt Jody is imprisoned. And I've disaggregated these risk curves. Oh, so let me start with the axes. So the y-axis is just the probability of Aunt Jody going to prison, or any particular member of your family going to prison. On the x-axis is the focal ego, the individual, as they move through ages. And I've disaggregated the risk profile into their kin-specific components. So we see how at each age, what proportion of that risk is due to what relation going to prison. Okay, and because these y-axis scales are different, I've superimposed the total white kin incarceration risk onto the black kin incarceration risk plot here. And so it's this entire thing kind of squished into there. Okay, so in terms of the distribution of kin types by age as a proportion of the total risk, there's not much difference between the white and black populations. But clearly there is a huge magnitude difference in that risk. And so if you want to get a sense of what this magnitude difference looks like, we can simply maybe take the average of the annual risk across all ages and just compare those numbers. And if we do that, we see that over the course of life, typical Black American experiences the first incarceration event of a relative on average 6 times more frequently than their white peers at each age. Okay, and if we wanted to take the point of widest divergence and look at the difference there, and that occurs at age 7, we see that the typical Black American experiences the first incarceration event of a relative on average, or not on average, just at 11.5% risk versus 1.6% risk. And that's the difference between about 1 in 10 relatives versus 1 in 100 relatives. Okay, so what I showed you there in those previous plots was a plot of incidence. So it kind of tells you about the distribution of these shocking events when Aunt Jody goes to prison over the course of your life. What I'm showing you here now is the prevalence of ever incarcerated kin within your total kinship network. And this is more a measure of kind of the enduring burden of having those members in your family network. And so on the y-axis, instead of risk, we have proportions ever incarcerated. And I've again disaggregated those proportion curves into their kin-specific components. And the first thing we notice is that extended kin, those kin that are typically not recorded in the data in these types of studies, represent the majority exposure over the course of life to incarceration within the family. And so this is not unintuitive because, right, there's more aunts and uncles and cousins than there are going to be grandparents, parents, and siblings. And yet, because of the data constraints, this is a fact that is often undermarked in the literature. Okay, so what we're going to do now is we're going to draw a line at age 21, the age of majority. And we're just going to look at how prevalent incarceration is within kinship networks at that age. So by the time that typical Black American reaches adulthood, 14.6% of their relatives are currently or have ever been incarcerated versus 3% of a typical white experience. Okay, so let's look at some results having to do with reintegration support. And so they're called we're now shifting to the boom cohort, or the parent generation, and we're looking at this from the perspective of the reentrant, the former prisoner who is now returning to their families. And so what we're seeing here is the exact same type of plot, where we're plotting prevalences, but I'm narrowing the field to those kin who are of prime working age. And we say that's between the ages of 25 to 54. And we pick this slice because we figure if anybody's going to be able to support you materially once you're out of prison, it's going to be kind of these folks who are able, if not employed, they're able to be employed and maybe be more useful than someone who's 5 years old. So what we do now is we draw a line at age 31 instead of 21. And 31 was the mean age of release in 1990, kind of at the height of the prison boom. So the typical Black reentrant returns to a family network where among their prime working age kin, 11%, about 1 in 10 relatives also have a prison record. Whereas the typical white reentrant faces something like 2.6% in their kinship networks among those who are working age. So I would argue that this makes a big difference, not just because these folks are unlikely to have jobs, those who are incarcerated, but because they are also people that your family is supporting at the same time that they are trying to support you. Okay, so to end, I'd just like to, in light of kind of what we've seen, just to reiterate a couple points. First, incarceration is a burden that is rarely borne alone. It affects the lives and livelihoods of friends and family. 2, the mass incarceration movement of recent decades has dramatically expanded the reach of the carceral state as the American family. And 3, this expansion has taken place overwhelmingly within the Black American family. Thank you.
Okay, we have 90 seconds for questions. What could be more discouraging? Okay, we have 3 minutes for questions. Marguerite?
I have a question about the simulation. Do you have the same? Do you assume the same rates of fertility and mortality in? Do you assume it's uniform in the population, or do you?
They're race specific.
But they're not incarceration specific, right? Because the idea is that you're more likely to be incarcerated if you have a small social network, and if you have, or a kin network, and if you don't have a large.
Yeah,
so
we
also previous correlation.
Yeah, what we do currently is we don't assume that rates differ very much, depending on your incarceration status. And there's some evidence to show that this is actually the case, that at least your fertility rates remain similar within and outside of prison.
Yeah, no, but the idea was more,
we have to stop you, Marguerite, sorry. One other question? Danny?
I thought it was very interesting. Maybe I don't know, not on the simulation, but on the setup.
Yeah.
It seems like it might even start smaller when we talk about the effects of incarceration. The first one is just that punishment's not fun, and it seems unjust, and there's not a good reason why blacks are incarcerated so much more. A lot of research supports that. And then there's one that says that coming out of prison is really hard for the guys who have been to prison themselves. That is, the punishment lasts much longer than we thought it would. And then there's the sort of collateral consequences on family members, and then you've got the collateral consequences for kin networks. And I always felt like that was enough. The reintegration stuff is interesting, but to me felt a little less intuitive than the collateral consequences side of it.
Thank you.
Next up, we have Monica Alexander.
Hello.
Oh, Monica. Monica is getting a PhD in demography. I should say Paul is taking his oral exams next week. And Monica just took her oral exams last semester. earlier this semester?
Last week.
Last semester. Take it away, Monica.
Okay, I'll try and be quick, which may mean I have to skip slides, but you know, this is why we have practices, I guess. So I'm going to talk about a model that we've been developing to estimate age-specific mortality rates at the subnational level. This is joint work with Emilio Zagani, who's at University of Washington, Seattle, and Margalit, who's got a joint position here, and at ENED. I just say ENED because I can't pronounce. Okay. So the motivation for this project was to extend the human mortality database to countries with less reliable data, and also to be able to produce mortality estimates at the subnational level. This particular project and this particular model focuses on the problem of estimating age-specific mortality by sex and county in the United States. So, what's the problem with estimating age-specific mortality at the county level? Well, there's a large range of population sizes. Some are really big. The largest is LA County with over 1 million people, but there's quite a few small ones as well. So about 10% of counties, or about 300 counties, actually have less than 5,000 people, and 1% have less than 1,000 people. So why is small populations a problem when you're trying to estimate mortality? Well, if we think about the death counts that we observe as some sort of realization as an underlying mortality process, the smaller the population, the more likely we're going to observe higher or lower deaths than what we expect due to stochastic variation. So just to illustrate that issue a little bit, so this is the mortality rate for all ages for California. It's plotted on the log scale. And so California's population, this was in 2010 for males, so California's population is about 38 million. If we pretend that, you know, maybe someone you don't like got elected as president and you all decide to move to Australia or something, if we pretend that the California population shrunk to 10,000 people, this is trying to illustrate what might happen to the observed mortality rates. So the black dashed line that you can just see underneath is the true mortality rate. And the three coloured lines represent 3 different simulations of that true mortality rate with a population of 10,000. So you could think of this as like observations of 3 different years. So you can see that there's a fair bit of fluctuation around the true mortality rate. And where there's gaps in the curve is where the observed death counts were 0. So we get, on the log scale they don't show up, and so we don't really have any information about the shape. The picture gets even less clear when you go down to 1,000 people. Again, this is 3 different simulations with 1,000 people, and at these really low ages we really don't have any information about the shape of the underlying curve. So this is the problem that we're trying to overcome, and so we're building a model to develop sort of robust estimates of mortality rates. So, like all good demographers before us, we're going to take advantage of the fact that mortality in human populations shows a fairly regular pattern over age and tends to change pretty gradually over time. Our model framework has essentially 3 parts, which I'll explain in a bit more detail. The first part is this underlying parametric structure which aims to capture basically the likely shape of the mortality curve. And then on top of that, we pull information about parameter estimates over space and smooth over time. So just to be clear, that our goal is, so we have death counts at age X in area A at time T. We assume that they're Poisson distributed with a rate that's equal to the population times the mortality rate. We observe the death counts and the population counts, and what we're trying to estimate is the mortality rates. Okay, so the first part is this parametric model that aims to capture age irregularities in mortality. So we could have chosen something like a brass model, which has 2 parameters, but we we decided to go for something that has a bit more flexibility. So this is modelled on the log scale. Mortality rate is modelled as a linear combination of 3 principal components. And the principal components are derived from some set of standard mortality curves. And so the idea here is that different linear combinations of these principal components, with different linear combinations, you can sort of express a wide range of different mortality curves. So, just to illustrate that, these 3 graphs show the first 3 principal components of a set of mortality curves for the US from 1980 to 2010. So we get these via singular value decomposition of the matrix. And you can sort of see that the 3 principal components have demographic interpretations. The first one is sort of like an overall shape of a mortality curve, so we sort of interpret that as baseline mortality. And then the next 2 allow either child mortality or early adult mortality to be higher than the baseline. So this is the first model model. So, which is this bit here. And so what we're trying to estimate are these beta terms. And so the second part of the model basically pulls information about likely parameter estimates over geographic space. So instead of treating each area as a separate population, we assume that the parameters for a particular area are a draw from a bigger common distribution that's a statewide distribution. And so there's a statewide mean and some sort of variance parameter. And so what happens is if we have the smaller the area, the more like the closer their parameter estimates are to this statewide mean. And so in that way, mortality patterns are partially, in smaller areas, are partially informed by the larger counties. So this is just illustrating the effect of this pooling. This is the same, so this is simulated data, so we know the true mortality curve that's shown in the black dashed line. And then the line with the dots is the simulated data, so that's what we observe. And so this was for a county with 5,000 people, so there's quite a few gaps in the log mortality curve. The red line and associated shaded area is the model estimate and uncertainty interval. And so on the left, this was a model that just treated every area separately. And so because there's a lot of 0 death counts at lower ages, the parameters try and fit a really low young age mortality. When you put in a pooling structure, the mortality is informed by mortality in other counties, larger counties, and so the young age mortality is pulled up closer to the mean, to the true value. Okay, so finally we have this, we assume smoothing over time of the parameters, so we assume that mortality changes fairly gradually over time. And so the way that we impose this assumption is by penalising the second order differences in those mean parameter values. So penalising the second order differences is essentially penalising fluctuations from a linear trend over time. And this is how we impose this penalisation. So we assume that the second order differences are normally distributed around 0 with some variance parameter that's estimated in the model. And this figure is just showing the effect of smoothing. So the blue line, which is sort of fluctuating, is the model with, without smoothing assumption, and then the red dashed line shows the effect of smoothing. So it essentially becomes closer to a linear trend. Okay, so this is just the full model. I didn't talk about the random effect, and I even forgot to mention it. Whoops. So in the underlying parametric structure, we actually add a random effect, and this is basically to allow for over dispersion. So the fact that observed death counts are often, the variance in observed death counts is often greater than the mean, which wouldn't otherwise be allowed with a Poisson framework. Okay, and it's fit in a Bayesian context, and so we put uninformed priors on all the variance parameters. So I said at the start that this was, the idea of this project was to estimate mortality rates by county, but we don't actually have the data yet. So this is, the model was tested on simulated data that was meant to mimic US counties. So this is just illustrating 3 different counties within a state. Left to right, the population is increasing from 1,000 people to 100,000 people. And so you can see the effect is that we basically observe more information about the mortality curve, and as a result, the uncertainty intervals get a lot more narrow. Because we didn't have US county data, Margalie kindly provided data for the French departments from 1975 to 2008. So these charts are just illustrating the fit to 2 different departments for 2 different time points. So 1975 on the left, 2008 on the right, and the top county has about 37,000 people, so the uncertainty around the estimates is a lot greater than this guy who had about 270,000 people, or males I should say. Once we have the mortality rates, we can easily get other columns in the life table. So this is life expectancy at birth for 2008 for males. The lighter colour shows higher life expectancies, so it's highest around Paris, which is this tiny area up there, and I think this is Toulouse, down here sort of.
Somewhere
The land of sausages.
Yeah, well, they should have had that. Okay, I can skip this, or should I just...
You have 2 minutes.
Okay, so just really quickly, this is just to illustrate that as well as mortality information about mortality rates, the model, we also estimate these variance parameters, which in itself could be interesting in studying mortality changes over time. So this is showing the variance parameter for beta 2, and I'm sure you all remember that beta 2 was related to the principal component that was child mortality. And so what this graph is saying is for French departments, the variance in this dimension of mortality is increasing over time. So the departments are getting more different over time in relation to child mortality. So this is just illustrating 2 departments that are quite different. This on this dimension, so this is a low value of beta 2, and this is a high value of beta 2, and you can see that it affects the level of infant mortality in relation to other mortality. So I think that these variance parameters could potentially be useful in looking at these changes and seeing what might be driving them. Okay, so to summarise, we developed this model framework that sort of has 3 parts. Takes advantage of age regularities of mortality, and then pulls information across space and smooths over time. We tested it on both simulated and real data, and it seems to give reasonable results and uncertainty levels. And the next stage is actually getting the data and coming up with estimates by US counties. And just quickly, there's quite a few people in this room who have heard way too much about this project, but I really, really appreciate all their feedback, and it's been really good. So, thank you.
Ron?
I have 2 thoughts. Very nice, thank you. I thought the smoothing over time looked like it might be excessive, just eyeballing it, and one thing would be to say compare it to annual E0 at the national level and see, because there have been some non-linear trend-like changes, particularly by sex.
Yep.
So that's one thing. The other thing was that I think there's systematic changes in the age shape of mortality as the level falls, or in relation to E0.
Yeah.
I don't know whether those are worth trying to pick up, or whether you find any evidence of that, but that would be another idea.
Yep. Not yet, because we haven't really tested it on. I think US might be a bit different to France. Yeah. Thank you. Okay.
As you move forward, it seems to me you'll want to make the geographical dimension more sophisticated. since Los Angeles is not the best comparator for Bakersfield.
Yeah.
In some ways, this using states as your geographical baseline is missing much of what really varies in mortality.
Yeah, so actually to that point, I didn't mention it today because I was rushing, but in the paper we sort of stressed that it's flexible in a sense that it doesn't have to be the state means. You can sort of decide, based on your context, you can decide maybe it would be more appropriate to have different means around rural versus urban or around certain age structures or things like that. But definitely, as we move forward, building in sort of covariances across adjacent areas or distance will become more important.
A policy question. You produce a number for Yolo County. I'm really interested in heroin deaths or something, so this deaths among, say, 20 to 30-year-olds where normally people aren't dying. And you have an estimate, and then I see how many deaths there are. And why should I pay attention to your estimate since it's not based on how many people really died in that county? So I can see how this is going to be used, right? There's going to be surplus deaths in different counties in the United States. And there's going to be a debate about whether how many people really died versus how many people you smooth, you think should be done. How do you deal with this in terms of a practical consequence of people pointing out, say, deaths in these ages which are so political right now?
Yeah, I think it's just important to, putting uncertainty around estimates I think is important in itself because, okay, maybe if you know, like, exactly there were X amount of heroin deaths in Yolo County, but often you don't know that, and I guess it depends on what you're trying to measure, right? Are you trying to measure annual deaths and then attribute some reason for those by year, or are you trying to get an idea of some sort of underlying mortality structure, which is subject to stochastic variation from year to year? So I guess sort of making...
But even if we're interested in the actual number of deaths, you're saying that the inference from that you should be careful of because this could be compatible with all kinds of regimes in a small county.
Yeah.
Great. Thank you, Anka.
Oh,
sorry, Dennis.
Okay.
we can talk later.
Yeah.
Dennis, ask your question.
Oh, well, I was gonna, so this is, what I think would make your argument more powerful and might sort of be related to this point is that I think a fair question is what would you do instead of this? And what people would typically do is pool these counties over time to get enough. And so you could probably show that your model is more informative versus that standard as opposed to, if you can count heroin deaths and that's what you care about, then obviously you just look at heroin deaths. So if you had like a comparator that was more concrete and really what people would do in the situation, I think you persuade them that the machinery is worth it.
Yeah. Okay, thank you.
Thank you, Monica.
Okay, so I was told I have about 5 minutes to present this, so it was hard choosing material, but hopefully I cover a lot in a short amount of time. So the title of my talk is Estimating Subfecundity in the National Longitudinal Survey of Youth 1979 Cohort. And here I'm broadly defining subfecundity as a reduced biological capacity to reproduce. Okay, just a brief overview. This is a descriptive paper that's part of a larger question, investigating the processes leading to childlessness in the United States. And I'm particularly interested in how biology might interact with women's reproductive life course choices, including things like partnership, attachment to the labor force, education, etc. So I'm using the NLSY-79 data because it spans a cohort's complete reproductive life course. It has rich fertility histories, and it has a lot of data on other life course measures that I'm interested in. And unfortunately, though, subfecundity is not directly measured, so my first aim is to indirectly estimate, a measure of subfecundity that I hope will ultimately be used as an input into later work, and then compare this estimate with simulated data and estimates from other sources. Okay, so first a bit on measurement. What I do briefly is I rely on a set of measures collected every 2 years, and And basically, I think of women observed at each survey as being a member of each of one of these three states. So this is using a multi-state model framework. So a woman is either observed as trying for pregnancy, not trying for pregnancy, or is pregnant and has a child. And so this last state you can think of as an absorbing state. And then I consider a woman trying for pregnancy if she meets these three criteria, if she is in a partnership, if she is not using contraception, and if she expects a child before the next wave. So I'm interested in transitions between these possible states across waves, and particularly I consider a woman to be subfecund if she is in this trying for pregnancy state in 2 subsequent waves. And just to compare with other measures of subfecundity, I'm sure most of you are aware with clinical infertility, which is defined as at least 12 months of attempting pregnancy without a recognized conception. So this is going to differ from my measure. And to demonstrate, I have this graph here with 2 surveys in the vertical line, so survey 1 and survey 2. These are 24 months apart. And then I have 3 individuals, A, B, and C, and each individual has a line that represents their length of pregnancy attempt. So both A and B, let's say they tried for 13 months before conceiving. They would be clinically defined as infertile. However, as you can see in survey 1, I only observe person A as trying, and then for person B, I don't observe at all because this episode happened in between 2 survey points. However, for person C, I observe them as trying in survey 1 and survey 2, so this person I consider as subfecund. Obviously, there are differences between a measure of clinical infertility and my estimated measure of subfecundity, but it's a measure nonetheless. Okay, so just some initial results. If we think about using this multi-state framework and looking across survey waves, we can calculate a transition matrix. And I'm interested in this first row here, which shows the probability of moving from a starting state of trying to these other states, or staying in the trying state. So on the top right-hand corner, we see the probability of moving from trying to having a child is 31%. What I'm interested in is staying in the same state, so from trying to trying is 37%. So this indicates that there's variation that I can tap into in this survey. As a validity check, what I can also do is look at waiting times to conception, since first observed as trying among women who I know ultimately do give birth. And we see here this distribution, and on the x-axis is waiting time in months, and this is 5 years. And we do see this gradual decline with some variation. And what I've done is I've fitted an exponential model to this data, and I find an estimated rate of 0.13, which translates to an average waiting time of about 7.5 months to conception. This does differ somewhat from other estimates of waiting times to conception. For example, one estimate is a rate of 0.2, which translates to a waiting time of about 5 months. And I forgot to mention too that this exponential model approximates a model of homogeneous fecundability. So this doesn't address any kind of underlying heterogeneity in the population. Okay, and then lastly, I have 5 minutes. I have a comparison here. So first, in the first box, I have lifetime prevalence. So using my indirect measure, I can see among women who I do observe after age 40, how many have ever experienced my measure of subfecundity, and that's about 7%. There's no comparable measure in the literature. However, I did find that 21% of American women experienced at least 1 episode of 12-month infertility in their lifetimes. And then lastly, when we limit it to childless women, we do see more of a correspondence perhaps with other sources. So I find that among women who I know are permanently childless in the NLSY, 42% have this episode of subfecundity. And in the NSFG, we find that 40% of women aged 40 to 44 are classified as involuntary childless. And that's it. Thank you.
I wonder if you have enough power to do your exponential model with covariates in particular age.
Oh yeah, so I have stratified by age, and there's not a lot, unfortunately, at the older ages.
I also wonder if you could consider maybe getting more power by combining with the later NSY?
The 97.
Yeah.
So there aren't child expectation measures. But there are contraceptive use and partnership measures that could be used. But those are exist. Yeah. Ron?
Based on your very nice little diagram of the intervals, this looks like it might be super subfecundity or something like that.
Right.
And then it would be interesting to know, maybe through modeling or looking at a fuller data set, how it's related to a standard subfecundity.
Yes, and that
Half
is,
as prevalent or?
that's the next step, is to do it running simulations and,
Okay,
yeah,
thank you.
great. Yeah. Oh, sorry, Madam, yeah.
Yeah, so you started by saying this is part of a bigger project on
Yes.
childlessness. So
Yes.
it'd be interesting to have just a quick note about how much of childlessness is attributable to biological unfecundity.
Just in
Or
general,
involuntary.
from previous studies,
Yeah, or
Yeah.
if you've done some
I haven't quite yet.
investigation.
Yeah. Jenna, do you have
Oh, I was
something?
just gonna say, it's probably worth mentioning availability or lack thereof of ART for this cohort.
Yeah, great. Yes, David, right? Did you have a, no? Okay.
Last chance to have your hand up? You don't want to ask? You can ask, it may not be answered. David, did you?
I saw a hand, but it's,
No, okay.
okay.
Great, thank you, Alison.
Hello everyone, so I'm going to present here this paper about health transition in Brazil, regional variations and convergence and divergence in mortality. So this idea of health transition is in the context of this health transition theory and its critiques to the epidemiologic transition theory, especially regarding to this idea present in the epidemiological transition theory that there is a unidirectional and linear process of changes in mortality, and then it's called prolonged polarized model, which is actually the example of the model which we observe in many middle income countries, in this case especially in Brazil. So it's a kind of a double burden of disease, but it highlights that it's a prolonged, it's a long time period. And also this convergence idea present in the both demographic transition and epidemiologic transition theory, it's not always true, and there could be some divergence and convergence over time. So what I'm going to do here is to analyze the mortality trends for the 5 major regions in Brazil, given the high inequality in the country, so we can see how it works, and then decompose the changes in life expectancy over time by age groups and causes of death, to try to explain the difference, the trends in life expectancy due to causes of death and age groups. So here is the life expectancy at age 10. I choose at age 10 just to exclude the influence of infant mortality, and we can see a long-term trend in convergence trend, and then more recently the more developed regions diverging from the less developed regions. So this is for males, and then we are trying to explain this long-term and recent trends. And this is for females. We can, if we look at individually for every region, we can see this divergence and convergence process, but it's less pronounced than the one observed for males. And here there is the composition results. In the y-axis we have the contribution to changing life expectancy at birth, and here we have the age groups, and the colors, the bars with different colors are the causes of death. So we can see this is the southeast region, which is one of the most developed regions. We can see in the 80s, here's 80s, 90s, and 2000, a large contribution due to infant mortality to increasing life expectancy, and these values tend to decrease. And there is also a shift from infectious and parasitic diseases, which is this red bar, to the mortality related to perinatal period, perinatal causes, especially cardiovascular diseases and respiratory diseases. The same thing for females. We also see different trends in the 80s in this region. Mortality due to external causes among adult males contribute negatively to the change in life expectancy, and here we see an incredible decline in mortality due to external causes, which represented most of the increase in life expectancy at birth. And we can also see for the elderly an important contribution to cardiovascular diseases, which is the green bars, which are the green bars here. This is for males and for females. This is for the Northeast region. I don't have cause of death because of some data quality issues, and I just show the results for the contribution due to the ages, but we can generalize we can infer some causes of death results as well. So we see that even for a more recent period, infant mortality is still important in the explaining the decline in life expectancy, explaining the increase in life expectancy, but in the other way, we have in the more recent period an increase in mortality due to external causes, especially among adult males. And even for the earlier decades, we don't have that much improvement in the mortality among adult males, especially. So this is part of the explanation of this recent divergence. On one hand, the increase in life expectancy due to the decline in mortality due to external causes in the Southeast region, and then an increase in mortality in the Northeast region. And also, we can see that these bars are the contribution due to decline among the elderly population. It's less pronounced than the Southeast region. So basically, this recent divergence trend can be explained by the external causes and also from cardiovascular diseases, mainly among the elderly population. So, just to finish, I'd like to say that in order to see a new convergence process, we have to deal with both groups. These less developed states have to try to decrease their mortality due to external causes and also act among elderly population, especially in mortality due to cardiovascular diseases. That's it. Thank you.
Thank you, Gabriel. Can I start? I was surprised by your conclusion that these two things are related, since usually we think of something like cardiovascular improvements diffusing, and people borrowing from neighboring districts and things like that, whereas something like violent death or whatever this is being a kind of a local problem. So does the correlation give us some insight about, say, just the generalized effect of income, or have you thought about, was this a surprise to you that these were connected, or did you expect?
Yeah, it was, I think it was a surprise because there are two things. The mortality due to external causes it happens in all the regions, even poor and more developed regions, but they are very dependent on violent deaths, and this is very dependent on local policies, so we can clearly see in the regions that there were some specific policies against violence and the mortality decline. So it's not exactly related to income, but in this case, cardiovascular diseases, it seems to me that it was more related to income, and the more developed regions were able to use all these technologies and cardiovascular revolution to improve their health conditions.
I think your big story is why the convergence and why the divergence, right?
Mm-hmm.
I suggest that you might want to look at the Southeast and at least initially take away the causes of death so it's strictly comparable to that you've got there, and put them on the same graph. say males, and you can look, because I think the story here is in external deaths.
Yeah.
I think, but it would be very interesting then to see them say males on the same graph, so you can compare the southeast and the northeast, and see what comes of that. And I think that will give you a key, because it looks to me like the march of development, and it is much further advanced in the southeastern part of Brazil than it is in the northeast.
Yeah.
Just a suggestion.
Yeah. Oh, that's a good idea. I have done this, but it's.
And then use that later, because that's very rich and very lovely, but you have nothing to compare that with your other ones, the northeastern part.
Okay.
Along the same lines, just as a suggestion, the patterns are so different for the elderly than for the not elderly. So you might want to actually segment your presentation in that way. I don't know if that's accurate, but it seems to me to be, at least in, both in terms of the rate of decline, but also in terms of the causes of death. So there's different stories there.
Yeah, that's true. The things that, this is the contribution due to the life expectancy at birth, so I have to show you the same graph, all the ages, but I can think about trying to divide that.
The other thing you can do, since you're interested in the comparison between these two regions, is instead of showing, decomposing the difference in life expectancy at birth between two time periods for the same region, you could decompose the life expectancy at birth by age and cause, obviously, but between the two regions at two different time periods. So you have one single graph that would tell you in these two time periods or three time periods, that early on and then when there is convergence, and then at the end when there is divergence. What the difference are.
Yeah, I have done this. The things that these are 6 graphs for just one region. I have 5 regions, so 30 graphs, and I've done all these comparisons, and it's interesting. It's also interesting comparing every state at the same year, at every region at the same year, but it's also comparing every state at the same life expectancy at birth level. So we can see the southeast region at this in 2000 had this roughly the same life expectancy at the northeast region in 2010, and if you compare these contributions, they are, even though they have the same life expectancy at birth, they have different age pattern, which explains not just they are late, they are going to achieve in the future the same level as the more developed regions, but they have different patterns.
All right, thank you very much.